Okay, this is Mr. Nagy's Physics 11 class. We're moving on to our second unit of study. Although we've touched on it a little bit, we're talking about accelerated motion now in Physics 11. So we've done an activity in class as we finished up our uniform motion test. And with our activity that we did, it looked something like this. We took a cart, we attached a string over a pulley, and because gravity, and I'll put F subscript G there for gravity, acted on this, it caused this whole, we would call this a system of objects. Things that act together form a system. They all accelerated together, and we attached a piece of ticker tape here to this cart. We did kind of, for comparison's sake, show that the rate of acceleration, right, if I were to drop the mass right next to it and it wasn't attached to a piece of string, this one here would go down a lot faster than this one. Now, acceleration, it's a difficult topic. It's a difficult thing to see. We tend to think we have a feel for what acceleration is, and I'm going to put a little bit of a disclaimer here. Acceleration does not mean going fast. And where do we get that idea? So many students get that idea because you step on the accelerator of your car to go fast. We know that pedal is sometimes called the accelerator, and that leads to all sorts of problems, right? Acceleration does not even mean speeding up necessarily. It can mean speeding up, but not exclusively, okay? Acceleration is simply dealing with a change in speed or a change in velocity. Flip this here on. So here's the ticker tape that we got with our acceleration time graph, and I'll just post it on with what we were just looking at there. Our ticker timer tape, when attached to this, the dots start off fairly close together, and notice they're getting further apart, and every single time they're getting, and I didn't quite match them all up, they're getting a little bit further apart, right? There's a consistency to this. Now, this is the perfect case of physics. We're starting here at zero, and perhaps we're saying that's zero when we first let the thing go, and we're moving in this case, the rightward direction, and we'll just say that's in the positive direction. So when we graphed this, our graphs tended to look like this. Here's our position time graph, and again, the word position could be substituted with distance or displacement, and again, we need to remember the idea of vectors and scalar quantities. It still applies here. Acceleration, and if you remember when we did this, we said we didn't have a special word for it, but acceleration is technically a vector, but sometimes we'll consider it a scalar if no information is given about the direction of the acceleration, right? Here, everything's moving, I guess, in the positive direction. Nothing is explicitly stated about it, but our graph is going up in the positive direction here. Our velocity is going up in the positive, and we've got an acceleration time graph here as well. So we did a graph like this, our position time graph, as we measured out the displacement. Now, I've got down here sort of some data that I got from the Physics Classroom website. Now, this data is not specific to this case, okay? It's just kind of some random that I wanted to be able to take a look at the data and see what's going on with accelerated motion. So, back here, though, our position time graph is a parabola, okay, kind of a curve there. Information we can get off of this thing, we could always go and just kind of, what's the velocity or the position at this point in time? You read up and you read over, and so here at the 10-second mark, I might be at about 80 meters or thereabouts if I tried reading across there. Right? I can read at any different time. And as we saw last unit, if I wanted to find, if this is the only information I had about the motion of the thing, I could find the instantaneous velocity by finding the slope of a tangent to that thing. Now, more importantly, our velocity time graph. When we were dealing with uniform motion, our velocity time graph was a horizontal line. I drew that in there and I'll get rid of that. Now we see that our velocity time graph, in this particular case, it has a positive slope. It's increasing to the right. We could, of course, read off of the graph and say, what's the velocity at 5 seconds? Read on all the way over and up. What's the velocity at 10 seconds? So at 5 seconds, it might have been doing 8 meters per second. At 10 seconds, it might be doing 15 meters per second. You can always read off the graph. But the key thing about this graph is not that we can read off of it, although we may want to do that on occasion. The key thing here is it's a linear relationship. It's of the form y equals mx plus b, so we can find the slope. And the slope is equal to your change in displacement, your change in velocity over change in time, right? There's a change in velocity if I'm picking this point here and this point here, and there's a change in time. The rise over the run, if you will, and that is equal to the acceleration. I'll put up here, acceleration is equal to slope of a velocity time graph for a linear relation like this. Right? Key thing is, the slope is exactly the same here, as it is here, or anywhere along there. It's a uniformly changing velocity. Okay? And if the slope is equal to the acceleration, and the slope is the same everywhere, then the acceleration should be the same everywhere. It looks like the slope here would be 2. Reading up on this graph, it's always 2. Something to bear in mind as you finish up that acceleration time lab. Okay? Rather than try and figure out between data points like we had down here, right? When we graph it out, if we have any error, and we certainly had error in our dots on our ticker tape, it's not the perfect world of physics, our acceleration should be uniform. Okay, so back down here to this one I was just scribbling upon. Let's take a look at our a data table for this. In the first interval, the second interval, so it might be from here to here. I don't know, whatever as its second is. It depends on the period of this particular ticker timer, and we don't know what it is necessarily. So we've got time intervals of 1 second, and there's another second. So this is our second, and then there's another one here, 1 second, and this is our third, right? And this is our first. So 0 to 1, 1 to 2, 2 to 3, and so on. Our average velocity is the displacement during the interval divided by the time of the interval. So that's a 1 second interval. So I traveled 5 meters, we're saying in here, my average velocity was 5 meters per second. In the second interval, I traveled further, right? I went about 15 meters according to this. Again, it was a 1 second interval, so my average velocity was 15 meters per second. In the third interval, I traveled 25 meters further than the 15. Again, that was still a 1 second interval, so my average velocity during the interval was 25 meters per second. So the thing is, we're changing our velocity each time. I went from 5 to 15 average from the first interval to the second interval. I went from 15 to 25 in the next interval. I went from 25. Our velocity, our change in velocity, is about 10 meters per second every second. Looking at that, we can see a running total over there. So here's a key thing about our unit for acceleration. Let's get away from the red here. Acceleration units it's meters per second is our most common unit. But that's a little bit messy. It's a fraction within a fraction. We've got a fraction in the numerator over a decimal here. And remember, whenever it's just like meters per second divided by seconds when you put it over S. And whenever you divide by something, it's the same to multiply by the reciprocal. So I could go meters per second times 1 over second is the same as that. Meters times 1 is meters. Seconds times second is second squared. That's kind of our most common shorthand method of writing down acceleration in terms of units. With a car, we might want to talk about kilometers per hour per second, okay, when you accelerate on the highway. Now, here's the thing. When you're accelerating in your vehicle, you usually accelerate for 8-10 seconds, even if you're at a stoplight and you're getting up to highway speeds of 100 kilometers per hour or thereabouts, right? You don't accelerate for much more than 10 seconds, 8 seconds, maybe 15 seconds. You can get up to our typical vehicular speeds in that kind of a time. So we don't talk about kilometers per hour, because if we accelerated at the rate we do so in city streets or on the highway in an hour, if we kept accelerating at that rate, we'd be doing thousands upon thousands of kilometers an hour. So kilometers per hour squared is not a unit that we're going to use in Physics 11, but we might see kilometers per hour a second. Our most common unit, though, is meters per second squared. Okay, so again, that's our most perfect case, simple enough, acceleration. Oh, one other thing we can get from this, of course, is we said in our last unit that, I'm just going to sketch a quick velocity time graph. If we had a velocity time graph that looked like this, then the area under the graph here, make a little rectangle, was equal to the displacement, because area is length times width, and the length here is your change in velocity, and the width here is your time, so it's velocity times time. I'm leaving the little change in signs out, and that, of course, is equal to your displacement or distance, depending on if we're talking vector or scalar. So the area under a velocity time graph is equal to displacement. That's still true here. The area, and here's our zero axis here, the area under here is still equal to our displacement, okay? Area is equal to the displacement during the interval. And here, though, it's not a rectangle, so it's 1/2 base times height for the area of a triangle. So it's 1/2 velocity times time, if you like, where your total change in velocity is about 25 and your time is 15. I'm not going to try and do it. It's really hard to read on this small table here. But we could figure out, using the exact same thing, the area underneath a graph. Now, come on, another page. There we go. One other thing I want to look at. Now, of course, we're going to move away from that perfect case scenario where everything starts at zero and moves in the positive direction. What happens if we've got an object moving in the negative direction? Okay, so we've got a velocity initially, I shouldn't say that, sorry, not in the negative direction, but with a negative acceleration. So looking at this graph here, right, and here the dots are further apart. Just going to get another. Okay, so this was here where the dots initially were further apart, right? So further there, closer and closer and closer. So when I started observing this object, whatever it might have been, it could be a car, right? A red car or something like that. It was moving fairly fast. And what was happening here was they're getting closer and closer together. It came to a rest. So now we've still got a slope to this line, right? And we can certainly calculate the slope, but it's going to be a negative slope. Our everyday lingo for this particular object, we'd say it's slowing down. WN. Okay? It's slowing down. But is it accelerating? Well, absolutely. Acceleration is a change in velocity, and our velocity is changing. It goes from 20 down to 0, right? So slowing down or changing our velocity here would be the same. Would still be an acceleration. The slope would still be our acceleration of this. Notice, if I wanted to draw my tangents, my instantaneous velocity, I'm fairly steep there. But if I go over a little bit further here on the position time graph, let's see, if I go over here on the position time graph, it's got a slope of 0. So steep, less steep, and so on. And the steepness, of course, our tangent on our position time graph does represent our velocity. Notice our acceleration here. It's always negative. It's always here below zero on the negative side. Looks like it's about 1.5 or something like that. If I found the slope of that line, it would probably be about negative 1.5. So what does that represent? It was going fast here and it's slowing down. Still in the positive direction, right? But our acceleration in this case is negative. Acceleration is negative, right? We got a negative slope right there. But our velocity is positive, always moving in that direction. Let's go back to that little animation. Okay, we're always moving in the positive direction to the right. Okay, we're just slowing down until we come to a stop. That's a negative acceleration, and negative is by definition to the left. Okay, something to think about and where we're going in this unit.